Hello, this video is to help you with homework problems 1 and 2 on homework number 8 for the course. Um, in this particular problem, we have a granite column. We don't know how tall it is, and that doesn't really matter. It doesn't really matter that it's granite either. What matters is that it's 6 by 6 in its cross section. And you're asked for some things that might seem a little bit confusing at first. It's asking you for the values and orientations of the planes for maximum tensile and compressive stress. It's also asking you for the maximum shear stress and its angle of orientation. Um, I'm not going to solve everything for you, but I'm going to get you started on the problem. Now, one thing that I do want to mention about the way the book is doing its convention for the angles is, as opposed to how I've done mine, is that the book is measuring theta with respect to the cross-sectional plane. I've measured theta to be this angle here in deriving the formulas in video lesson 17. You'd get similar results either way. However, I just want you to be aware that for the trigonometry expressions, the book is using this angle theta that the plane makes with the cross section as opposed to theta, which is defined this way right here in my video lessons. Either way is correct. The important thing in all of this is to understand that you have to resolve this force into its components and figure out the area of the oblique plane that the stress is being calculated on. So if I do that and I use the formulas that are in the book, which are the formulas that you will see pop up after you've submitted your homework the first time, I would have the cross-sectional area as A0 equals 6 inches times 6 inches or 36 inches squared. And sigma would be equal to P over A0 times cosine squared theta. So if I had, if I plug in everything that I know, I would have this result, negative 6.56 cosine squared theta KSI. So you might ask, well, where is that maximized? Well, that would be maximum when cosine squared theta is at a value of 1, because cosine theta can take on any number between -1 and +1. So we would want it to either be zero. We would want cosine theta to be either 1 or -1. And it would be equal to a value of 1 when theta is equal to 0 or when theta is equal to 180 degrees. So what that means is this plane of the original cross section, the plane perpendicular to the axis, is the plane where we would expect to see maximum stress in the maximum normal stress. Um, Now, if you were to think about the compressive stress, that's going to be highest when theta is equal to 0. If we were interested in the maximum tensile stress, which is why this is a little bit of a strange question, because there's actually no tensile stress, but there is a point at which sigma becomes minimized, and where cosine squared of theta is equal to 0. That would be where cosine theta is equal to 0. And that would be for a plane that is along this particular axis. You would have no tension or compression on this plane that is going down the axis of the member. So that's what they are looking for. So when you take a look at the solutions, eventually you'll find that for the maximum tensile stress, it's the minimum compressive stress, and that would be 0 at a plane of 90 degrees. So I just wanted to explain that to you and let you think about what that would possibly mean for you. All right, so I just wanted to take a look at the maximum shear stress as well. If I was to use the definition of theta, if I was to define theta in the way that the book does it, as opposed to the way that I did it in lesson 17, I'd end up with something that looks like this. So the shear stress is going to be given as the absolute value of P. In this case, I took P as negative because it was a compression. In this case, I'm not as concerned about that because I'm interested in the absolute value of the shear. So I would have P over 2A0 times sine of 2 theta, and I would have something like this final expression, or 3.28 sine of 2 theta KSI. And if you're interested in the maximum shear stress, you need to think about what's going to maximize sine of 2 theta, probably something around 45 degrees, or some angle at 90 degrees more or less than 45 degrees. So you would want to think about that in what's going to maximize sine of 2 theta, what's going to make that a maximum value or perhaps a minimum value, where it could take on plus or minus 1. So those would be the planes of maximum shearing stress in terms of absolute value. So I do want to just remind you that these results are different from what's been derived in the board notes, just because of where the book is measuring the angle theta and where I've measured the angle theta. So I just wanted to point that one out to you because that might be a little bit tricky or confusing. And in general, although there are formulas that can get you very quick answers, my advice to you in learning the material for homework 8 is to not think about formulas for maximum stress, minimum stress, sigma max, sigma min, or tau max, or anything of that nature. Or these formulas for stresses. Think about the problem in terms of basic definitions, resolve the force into normal and in-plane components, and figure out the area of your oblique cross section. And if you figure out how you would do that, if you go back to fundamental definitions, you will not go wrong. So, however, if you're more prone to make a mistake, if you're memorizing these, this is a set of equations, and you forget how they measured theta or how I measured theta. So for me, it doesn't matter if I'm not memorizing formulas like these, how I define theta, because I know that for a normal stress, it's a normal force divided by an area, or a shear stress is an in-plane force divided by the in-plane area. So if I'm always looking to do the basic definitions, I might not be able to remember this right off the top of my head, but it wouldn't matter because I would know the basic definition of normal stress or shear stress, and I could come up with these expressions anyway. I could go back and derive them on my own if I needed to. Not that I would almost ever need to do that, then you certainly probably wouldn't need to do that on an exam. But if you remember the basic definitions of normal stress and shear stress as a normal force or an in-plane force divided by the area over which it's acting, you'll do just fine with this homework problem.